Alright, let's continue then with this short contact mechanics lecture. And first of all, maybe you have tried the example from part 1 and maybe you found the result. So I just made some computing in MATLAB here to see what the answer is. I computed the effective elastic modulus as 206 gigapascals divided by 1 minus Poisson's ratio with power 2. That means that the elastic modulus is 226 gigapascals. The radius is 35 millimeters. The load 100. And I just compute the size of the radius of the contact spot according to this expression in the previous slides. And that means that the radius of the contact spot is 0.28 millimeters. So the diameter is approximately almost 0.6 millimeters. It's not it's very small spot, as maybe you expect also. This and the pressure is computed as also shown in the previous slide, according to this expression, and it shows to be 0.59 gigapascals. So with this ball, a ball of diameter 70 millimeters, and you press 10 kilograms weight approximately onto it, then the contact pressure reaches more than half a gigapascal. Still the spot is very small. So this is how you can use these pretty simple formulas to compute contact pressure. And normally you use this for ellipsoids like this. Normally it's a cylinder or a ball. That's the most common. Before moving on here, we can think about what is happening inside the material. What you maybe not expect is that the maximum stress occurs below the surface. That's especially for a friction-free surface or friction-free contact. So if this is the surface, and then you have your pressure, contact pressure here, Hertzian contact pressure up here, and if you compute the von Mises effective stress, or the effective stress, you will find that the maximum stress is some distance down into the material. This distance depends on the size of the contact, the magnitude of the pressure, and the etc. But it can be pretty far down, almost millimeters down into the material. Depends on the application. You may also compute the shear stress, and then you find that the maximum shear stress is close to the edges of the contact and also down in the material. When you add friction on the surface too, then this maximum moves towards the surface, and so that will definitely make the plastic deformation to occur closer to the surface and at the surface actually. But this is the plastic deformation is of course controlled by the maximum effective stress, so the plastic deformation starts down here. And there are some simple rules about when plastic deformation occurs, and as I said, it starts below the surface, and you may say, for at least for metals, that the mean pressure, it begins, the first sign of plastic deformation occurs at around a stress level, or a pressure, contact pressure level, which is around 1.1 multiplied by the yield stress of the material. Then when you increase the contact pressure more and more, then this plastic deformation zone reaches the surface, and that happens at approximately an approximate contact pressure of 3 times the yield stress. And if you keep on increasing the load, then the contact pressure can't increase anymore. It remains constant at this at the yield stress level, or it just makes the area of plastic deformation bigger, and that is actually the basis for hardness testing. So this idea is used when you make the hardness testing. So next slide shows that that if you press a cone, for example, which is sharp enough to, or a cone or a pyramid maybe you heard about Vickers hardness, then you use a pyramid, you press it down with a certain load, and this sharp corner creates plastic deformation, and you get plastic deformation in the whole plastically deformed zone, which leaves a permanent track after it. And afterwards you just measure the area of this mark, the plastically deformed mark, and you define the hardness as the applied force, which is 300 newtons, divided by the measured area. So, and that means for example, if you see somewhere a measurement or a hardness value of 400 HV, that means hardness Vickers. That means it's 400 kilopounds per square millimeters. It's old units, but if you translate that into SI units, that's the same as 3,900 megapascals, or 3.9 gigapascals of hardness. In a real surface, then you have a number of asperities, and the real area of contact consists of a number of small spots, and all these asperity contacts may be just small, can be fractions of millimeters sized spots. So we really must distinguish between the apparent contact area and the real contact area. Where the apparent contact area, and that's the whole zone contact area if the surfaces had been perfectly smooth, or for example two flat surfaces into contact with each other perfectly smooth, then the apparent or nominal contact area can be gigantic, but the real contact area is the spots where there is actual contacts. That's normally at the summits of the asperities. And this real contact area is normally only a fraction of the apparent contact area. So it can be could be fractions of percent normally. And this is a kind of theoretical view of the multi-asperity contact. If you press the surfaces into contact, you may find a number of contact spots like this picture. If you then increase the load a little bit, what you do is that each contact spot grows, but also more asperities come into contact. And for some surface roughness, you may say that the mean size of the asperity contact remains constant. So the individual spots grows when the load increases, but the size of the mean size of the spot remains constant. It's just the number is increasing. And that is actually creating a linear relationship between load and real area contact. So you can think about the friction law, like the Amonton friction law, Coulomb friction, is that the friction force is approximately the real area of contact multiplied by the shear strength of each contact spot. the strength of the spot, the stress required to overcome, to start sliding here in the contact. And if there is a linear relationship between load and real area, that means that the real area contact is a constant multiplied by the normal load, and then multiplied by the shear stress again. Then you can see that if the load is constant and the constant, that means that this is a mu, what we call the mu, the friction coefficient multiplied by the normal force. This is why we normally say that the friction coefficient is not a function of the normal load. This is not a general law, but it's good approximation. And this is a kind of explanation for that. On this slide, I just wanted to repeat that it's a good approximation of the real error contact in a multi-asperity contact. If you assume that well, if you think about the fact that the sharp asperity, asperity with high slope causes high contact pressure, and this pressure is high enough to cause plastic deformation, and then you assume that all asperity contacts are of this type, so all asperity contacts are plastically deformed, then you can claim that the contact pressure in each spot is the same as the hardness of the softest surface, and that's a constant. So the real area of contact is simply the ratio between the normal load, the applied load, and the hardness. And that's kind of a maximum. It's a reasonable approximation of the maximum possible real area contact in between two surfaces. There are many exceptions from this law, but it's a good first guess when you think about real area contact. Okay, if you want to do calculations yourself, you can of course use the formulas I have described in this short lecture, but you can also use the tribology ABC, which Anton van Beek developed, and the calculators you can find there. So please use them, and but of course, always when you use tools like this, you should also be aware about their limitations, and you should know how to do this by hand, not just trust computers. And just to show you some examples of what we have been doing here at the Lulu University of Technology is that we may study a real rough surface like this one. This is the undeformed. We can press it into contact with another flat surface and study how it looks like when it is deformed, plastically and elastically deformed. This is, for example, of interest when we study the contact between a seal and a shaft, or elastomer seal and a shaft. And finally, I just want to show you a movie showing two surfaces, two rough surfaces. Well, this is real roughness actually. It's measured roughness when they slide in contact with each other. So this is one surface, this is another surface, and down here you see the contact pressure. Let's run it again. So you see when the surfaces move, the pressure is fluctuating all the time. So even if you have a constant load, constant speed, in reality everything is moving. So this is something to think about when you think about contact mechanics and what is happening inside the tribological interface. So that's it. Thank you very much.